Hi folks, this is part 2 of the oscilloscope series, and the beauty of doing them in multiple parts like this is in part 2 I can tell you all the things I forgot to put in part 1. One of the things I gave short shrift to was the relationship between the time per division knob and the graticule of the scope. Now I did cover the volts per division or amplitude on the graticule, and the same theory applies. Each major division of the graticule is weighted by whatever the time per division knob is set for. So if you are set for 1 millisecond per division, each division is 1 millisecond. Or if I put the scope in 1 second per division, it would take a second for the dot to traverse from one major division to the next. Okay? And that brings up an interesting point, and that is the relationship between frequency and time. Time is reciprocal of frequency, frequency is reciprocal of time. Now, what does this mean? If we think about frequency, frequency is rated, or the unit of frequency is the hertz. And it's simply was named to honor physicist Heinrich Hertz. Before that, it was known by the more descriptive term cycles per second. And that's exactly what a hertz is. 1 hertz is 1 complete cycle in 1 second. Okay? So knowing that, it makes the time per division knob make a little more sense, because when we set it to 1 millisecond per division, and we feed in 1 kilohertz or 1,000 cycles, we will see 1 cycle for each major division. All right? So it's basically the fact that they are opposites or inverse to each other. The other thing I wanted to talk about was on digital oscilloscopes and aliasing. So let's take a look at the digital. Okay, so I have a sine wave on the scope. You can see it says it's about 45 hertz, and it's kind of dancing around a little bit. This is a problem. This is a phenomenon known as aliasing. And while it says it's a 45 hertz signal, I am actually feeding in a 100 megahertz signal. And this effect is due to aliasing. Aliasing is when you don't have enough sample points to give an accurate display. When we talk about sampling points, there was a very bright guy named Harry Nyquist, and he came up with Nyquist's theory of lossless sampling, stating you have to sample at twice the expected frequency to get any kind of fidelity. So I have 100 megahertz being fed in. Let's see what happens when I turn the time base, which is currently on 20 milliseconds per division. Now I don't have any divisions on here because I turned them off to get a better display on the scope. Let's see here. Let's turn the graticule back on. Is that what we want? There you go. Okay, so now I'm going to turn the times per division knob. And watch what happens. Now we have a stable presentation, and it says we have 100 megahertz. This is a problem with digital scopes. If you are unsure what you're doing, you can get yourself in trouble because you will be so far away from where you think you are. Okay, just want to point that out. I recommend getting an analog scope for your first scope, which is kind of a shame because these things are amazing, but you will know what you're looking at. A lot of stuff is buried in menus. In order to change the graticule, I had to go into a menu. In order to change the coupling, I have to go into a menu. Pop up my coupling menu, ground, AC, DC, menu off. On my regular analog scope, all I have to do is hit the knob. It's right on the front panel. most everything is. That's just something I wanted to point out. Now, the rest of this video is going to be about more advanced functions, and I'm also later on in the video going to set up about 3 or 4 different types of oscilloscope and show you how to do the same thing on different scopes. In other words, how to find the controls. All right, so let's get set up here and see what we got. Okay, the first thing I want to do is to show you how to set your oscilloscope up for 2-channel operation. This is something I very commonly do because I work on stereos, and I always put the left channel on the top trace and I put the right channel on the bottom. And I do the same thing the same way every time. If I'm using multimeters, I have 2 stacked, one on top of the other. The top one is always the left channel, the bottom one is always the right. I always tell people I'm training at work, do the same thing the same way every single time. And that way, if you're distracted, tired, brain dead, hungover, what have you, you're less likely to make a mistake. You're just going by rote, by muscle memory, if you will. So the top trace would be left, and we wanted to take a look at 2 channels at once. Now, I'm feeding the same signal into both channels with a simple Y connector. On this scope, I simply select channel 1 and then turn on channel 2, and I have 2 traces, 2 independent channels or traces. Okay, so I can put the one on top of the other, and it's just very handy. This way I can look at both channels at once and see if I have a problem. Like I said, I work on a lot of stereos. This works out well for me. Now, when you're in 2-channel operation, you may have seen, if you have an oscilloscope or if you've looked at the front panel, a button that says Alt or Chop. Now, this is kind of handy, and it doesn't really come into play until you're looking at more than one channel. What it's talking about is the sweep of the oscilloscope. Alternate sweep is exactly what it sounds like, and I'm going to slow the sweep speed down by turning the seconds per division to a lower sweep speed, and you'll see that we have one sweep and then we get the other sweep. Okay, they simply alternate. Now, problem with that is we get a lot of flicker. And I'm going to drop the frequency of my signal generator so this looks more like a sine wave. Let's see. Okay, but chop mode doesn't give us alternate sweep. It chops rapidly between both and helps to eliminate flicker. So when I go from alternate sweep to chop, our flicker drops dramatically. That is the function of the chop and alternate sweep buttons. I had no idea what this is for when I first started out, but it makes a lot of sense. Somebody took the time to explain it to me. Had they not, I might have found it in the manual, and I might not have. Anyhow, some of the other things that we see in 2-channel operation that we don't see in 1-channel operation is these 2 buttons, add and invert. All right, if we hit the add button, it simply adds channel 1 to channel 2. So if we have 2 divisions for each waveform, we will have 1 large waveform. Let's see. And you have to turn off, on this scope, you have to turn off both channels in order to get add. Now, if you add and invert both channels, what do you think you'll get? Well, if we add them together, we get channel 1 plus channel 2, but invert only affects 1 channel. And indeed, if you look at the display here, you can see our add is over here, and when I hit invert, this should go to a flat line. Now, why would that happen? Remember, if we're adding one and adding the inverse of the other one, it'll simply cancel out. So let's take a look at both channels with just invert. Now They look the same, but they are 180 degrees out of phase with one another. If I turn invert off, they are in phase, and they should lay one right on top of the other. If I hit invert, this is what we get. It simply inverts channel 2. Now, we use these to do something called pseudo-differential measurement mode. God, that's a mouthful. But basically, this is something we use to make measurements of floating or unbalanced amplifiers. For instance, I do a lot of work with stereos, and every once in a while, you will see a stereo that says, do not ground the speaker outputs, they are floating. And what this means is if you connect them up as I normally do here, or I take the ground clip from the oscilloscope or try to ground the scope as I commonly do with this guy, it's going to damage the amplifier. We were always taught when I was in school to float the oscilloscope, okay? And what you do here is you take your plug for the scope and you put one of these 3 to 2 prong adapters on it so that the ground is now floating. This is not recommended. This is a dangerous practice because it can leave your BNCs at a line potential or 120 volts. It's a shock hazard. So now we're shown to do the pseudo-differential measurement mode. And boy, like I said, that's a mouthful. So let's see what that's going to look like. Okay, so what I've got here is I have the output of my signal generator, and I have these 2 pieces of wire to connect onto. Now, in normal operation, we will ground our scope probe to the negative side and hook up the probe, and we'll get a good signal. And it looks like that. But if we can't ground it, we get this. And that is totally unacceptable. So what we need to do is do pseudo-differential input mode. So if I go add invert, turn channel 1 off, and take the channel 2 probe, we get a nice stable presentation. Now we have to make sure that both channels have the same volts per division setting, or else we get something like this. What happens is, instead of having ground, we have 2 probes, which will give us 10 megohm isolation and no danger of damaging the unit under test. And when we feed our signal in and we add an invert, we get a signal that looks like this. Instead of using ground, we're using the second channel as our reference. So you have to add and invert. Make sure both amplitudes or volts per division knobs are the same, and you can safely measure floating or balanced outputs. The other thing I want to point out on this scope before I set up multiples is there's a button that says bandwidth limit. Now, the whole purpose of this is a 150 megahertz scope, and I'm going to take both the inputs out, and we're going to look at channel 1 only, and I'm going to crank the sensitivity way up, and what you may find is you get noise. See how thick the trace is? That's just noise pickup, but when you have a probe on there, it can be worse. But if you limit your bandwidth, you get a much sharper, more defined trace. And if you're working on an audio amplifier, you don't need 150 megahertz, you don't need 20. So this will help lower noise. So that's pretty much all I want to tell you about the special functions, if you will, that you can do with pretty much any oscilloscope. One thing that this oscilloscope does that others may not is it does what's called cursor measurement. And I'm going to connect our probes back up again. Let's see. And I have to go here. If we have cursor measurement on, it puts these cursors on the screen, and I can move them into position, and then I can read my peak-to-peak volts right off the screen here. Your scope may or may not have that. Digital scopes you can just set up and it'll read it without having to use cursors. The other thing it'll do is it'll do frequency. I can move the cursors into position, go from one cycle to the next, and it'll tell me what my frequency is. I'm feeding a 1 kilohertz signal in, and it says 1.01. It's really hard to get an accurate measurement on an analog scope like this. They're not really a great tool for that, but you can see, you can get a ballpark reading. The other thing that this scope does that I absolutely love is it has presets. Now, I commonly look at both channels from the output of my distortion analyzer, and I have set it up so that I can just hit recall, set up both channels, 1 volts per division, DC coupled. Preset number 2 is channel 1 only, AC coupled. That's for taking a probe and probing around. Then I have some XY functions like this. That's for using a sweep. I have some XY functions for using, let's see here. This is for using my curve tracer, but it's a shortcut. And honestly, if you're just learning to use the scope, you don't need to use shortcuts. That's why I don't really recommend the use of digital scopes that much. I was talking to a gentleman, and I complimented him because he was able to get good readings with having very little experience. Then he revealed he was just hitting the auto button and letting the scope set it up. He was able to get waveforms, but he didn't learn anything about how the scope operates. And it's so important to know how something works. Anyhow, I'm going to set up multiple scopes, and I'm going to show you how to do the same thing on different types of oscilloscope. Okay, this pile here is 3 oscilloscopes. This is my O1 digital. This is a Tektronix 2213 60 megahertz, and this is a Philips PM3256 that was given to me. I don't even know what the bandwidth of it is, but it's a really nice scope. The case is totally destroyed, but the scope is beautiful. So we're going to start with this one. Now, this one has a little different panel layout, but all the controls are the same. Remember when we talked about coupling? We have AC, off, and DC. I hope you can see that well enough because I got 3 of these stacked up here. But this is what we're talking about. So I'm going to set this to AC coupling, and we have our sine wave. I'm going to turn our times per division to 0.5 milliseconds or 500 microseconds per division. And I'm going to turn our volts per division down to just give us a little more amplitude. Our Tektronix, we'll turn the time base to the same place, and we get about the same distance across the screen. And we have about the same amplitude. The difference is our volts per division is not calibrated because it is broken. So I just got the scope to repair. It's got focus issues, possibly power supply, and that's a problem. Then we go down to our digital. We're going to turn our times per division until we get 500 microseconds. Okay, and that gives us about the same display. We're going to change our coupling to AC. So on this, we have to dig through a menu. On this scope, our coupling is right here. On this scope, it's right here. They usually put the coupling by the input. They did it on all the scopes I've used, but on the digital, you have to dig through the menu. So we go coupling, AC, menu off. Coupling here, AC, coupling here, AC. Okay? If I want to look at 2 channels, on this scope, I go to both, and our second channel comes up. On this scope, we're looking at A, and if we want to see the other channel, we hit B. And if we want to see both of them at the same time, we hit alternate. There's our second channel. Remember, if we want to get rid of flicker, we can go into chop mode. That gets rid of our flicker. Alternate sweep, one sweep then the other. Chop, chops rapidly between them, gets rid of all the flicker. Not a problem with the digital. In order to see the second channel on here, we have to turn channel 2 on just by holding it. Now channel 2 is on. Okay. One of the other things I'm going to talk about is triggering from one channel while observing another, and I'm going to give you a demonstration of that. So let me stop right here. Okay, what I have here is a Hewlett-Packard universal counter, and what we're going to do with this is we're going to adjust the time base, and I'll show you how you go about doing something like this. On the back of the unit, we have our 10 megahertz out. And what we're going to do is we're going to put that into channel 1 of the Philips oscilloscope, and we're going to put in channel 2 the output of my GPS disciplined oscillator, which is also 10 megahertz. And we're going to adjust the counter until the time base on the counter agrees with the 10 megahertz from the GPS disciplined oscillator. And what we do is we look at our scope and we are going to observe channel 1. Okay, so here's channel 1. That's coming out of the frequency counter. If we look at channel 2 is the 10 megahertz from the GPS disciplined oscillator. So we want to leave our trigger on B, or channel 2, but we're going to look at channel 1. And as you can see, we don't have lock. So what I'm going to do now is I'm going to turn the adjustment on the counter until we get a good stable waveform. Now this pot's got some issues. And I wanted to replace it, but I want to give you a demonstration on how this works. As I turn this, you'll see we begin to get sync. And it'll never be perfect. You'll always have a little bit of drift. This pot is, like I said, has issues, but you can see that's about where we want it. And as it warms up, it's also going to change. You're supposed to warm these up for about an hour before you do this. Okay, that's still not right, but let's take a look at the counter. Okay. So if we look at the counter, and we take our 10 megahertz, you can see that's fairly close. This is our error. If we could get that to stop moving on the face of the oscilloscope, we would have 10.000 all the way out. But as I said, we have some problems here with our scope, with our counter, I mean. But that's what you do. You would put your reference in, trigger from your reference, and then set channel 1 until you get a stable presentation, not moving to either side. And that's why you would trigger off of one channel while observing another. Channel B, or channel 2 here, is our trigger. Channel 1 is depending on the trigger from channel 2 to get a stable presentation. Okay, I think I'm going to stop this right here because it's gone on a little longer than I wanted, but I hope you got something out of this. I enjoyed making the video, and as always, I love giving back to the community that has given me so much. Thanks a lot, folks.